When we gaze up at the night sky, we often imagine ourselves as solitary wanderers in an infinite cosmic ocean, with each star system existing in perfect isolation across the vast emptiness of space. It's a comforting thought in a way, that somewhere out there, ancient celestial bodies drift peacefully through the darkness, accompanied only by silence and starlight. But what if that serene solitude we picture isn't quite the reality? Tonight, as you settle into the gentle embrace of sleep, we're going to explore a fascinating cosmic mystery that challenges everything we thought we knew about one particular wanderer in our universe. The story of 3I Atlas, and the intriguing possibility that this distant traveler might not be making its journey alone through the cosmos. So close your eyes, let your breathing slow and deepen, and allow your mind to drift among the stars as we uncover what secrets might be hidden in the depths of space. Let's begin our journey by understanding what we know about this enigmatic visitor to our solar system. Take a deep breath and let your mind drift back to October 2019, when astronomers first spotted a faint glimmer moving across the star-filled canvas of space. 3I Atlas, officially designated C/2019L3, appeared to be exactly what scientists expected from an interstellar object. Picture it now as you settle deeper into comfort, a wandering comet born in the cold depths around another star system millions or perhaps billions of years ago. Like a cosmic nomad, it had been traveling through the empty spaces between stars, carrying with it the frozen remnants of its ancient home. The designation 3I tells us this is only the third confirmed interstellar object we've ever detected visiting our solar system. The first was the mysterious Oumuamua in 2017, followed by Borisov in 2019, and then Atlas. Each of these visitors represents something profound, tangible proof that our solar system is not an isolated island, but rather a port of call in a vast network of cosmic travelers. Atlas fits comfortably into our understanding of what an interstellar comet should be. As you breathe slowly and deeply, imagine this ancient wanderer approaching our sun from the constellation Lynx, following a hyperbolic trajectory that clearly marked it as a visitor from beyond. Its path through space painted the picture of a solitary journey, one object, moving alone through the cosmos, bound by the gravitational dance of celestial mechanics. The comet's composition appeared reassuringly familiar. Spectroscopic analysis revealed the telltale signatures of water ice, carbon monoxide, and other compounds we commonly find in comets from our own solar system. This suggested that wherever Atlas originated, the conditions there weren't so different from what we know. It was like meeting a traveler from a distant land and discovering they spoke a language we could understand. Atlas followed the expected behavior patterns as it approached our sun. It began to develop the characteristic coma, that fuzzy atmosphere of gas and dust that gives comets their ethereal beauty. As solar radiation warmed its ancient ices, the tail that formed behind it streamed away from the sun in exactly the manner predicted by our models, creating a gossamer trail of particles that caught and scattered sunlight like cosmic silk. Let your mind rest in this familiar picture for a moment. Here was a comet that made sense, that fit neatly into our catalogs and classifications. Astronomers could predict its path, analyze its composition, and file it away as another successful confirmation of our understanding of how the universe works. It was a visitor, yes, but a well-behaved one that followed all the rules we've spent centuries learning. The orbital mechanics painted a clear story. Atlas was moving far too fast to be captured by our sun's gravity. its trajectory carrying it on a one-time visit through our cosmic neighborhood. Mathematical models traced its path backward through time, suggesting it had been traveling through interstellar space for potentially millions of years before its brief encounter with our solar system. Even its size seemed appropriate. Estimates suggested a nucleus perhaps a few kilometers across, substantial enough to survive the long journey between stars, yet small enough to explain why we'd never noticed it before. It was, in every measurable way, exactly what an interstellar comet should be. The timing of its discovery also felt natural. As our telescopes become more sensitive and our sky surveys more comprehensive, we expected to find more of these interstellar visitors. Atlas represented progress, proof that our improving technology was finally allowing us to detect the cosmic traffic that had always been flowing through our solar system, previously invisible to our less capable instruments. Scientists could comfortably explain Atlas within the framework of stellar evolution and planetary system formation. Somewhere out there, perhaps hundreds of light years away, a young star system had gone through the chaotic process of planet formation. During this turbulent period, gravitational interactions would have flung countless small bodies out into interstellar space, creating a population of wandering comets and asteroids drifting through the galaxy. Atlas appeared to be one of these exiles, a fragment of some distant world that had been cast out eons ago to wander the cosmic wilderness. Its journey to our solar system was simply a matter of chance, one trajectory among billions that happened to intersect with our corner of the galaxy at just the right moment for us to notice. This narrative felt complete and satisfying. It connected Atlas to the broader story of how solar systems form and evolve, explaining both its presence and its properties within our established understanding of cosmic processes. The comet was unusual only in that it came from somewhere else. In every other way, it was a familiar type of object behaving in familiar ways. As you continue to relax, breathing slowly and steadily, hold this image in your mind. A lone comet, ancient and solitary, making its once-in-a-lifetime passage through our solar system before continuing on into the infinite darkness beyond. It's a peaceful picture, one that speaks to the orderly nature of celestial mechanics and the predictable behavior of matter and energy across the cosmos. But sometimes, as we're about to discover, the universe has subtleties that our initial observations don't immediately reveal. Sometimes what appears to be a simple, solitary journey through space carries with it mysteries that challenge our assumptions about what it means to travel alone through the cosmic deep. But as astronomers continued their careful observations of Atlas throughout its journey, something unexpected began to emerge from the data. Let your breathing remain slow and steady as we explore how this seemingly straightforward story started to develop intriguing complications. The first hint that Atlas might not be the simple, solitary traveler it appeared to be came from the most routine of observations. As telescopes tracked the comet's path across the sky, recording its position night after night, a subtle pattern began to reveal itself, one that didn't quite match the clean mathematical predictions of a single object moving under the influence of gravity alone. Picture yourself floating peacefully in space, watching Atlas from a distance as it moves through our solar system. At first glance, everything appears normal. The comet follows its expected trajectory, its tail streaming behind it in the solar wind. But if you were to observe very carefully, with the patience of deep space and the precision of our finest instruments, you might notice something curious. Tiny deviations in its path, almost imperceptible variations that seem to suggest the presence of something more complex than a simple, unified object. These deviations were subtle, so small that they might easily be dismissed as measurement error, or the natural variations that occur when solar radiation pushes against a comet's irregular surface. But as the observations accumulated over weeks and months, a pattern began to emerge that was difficult to ignore. Atlas wasn't moving quite like a single solid body should move. The anomaly became more apparent when astronomers began studying the comet's brightness variations. As you sink deeper into relaxation, imagine the gentle pulsing of starlight, the way celestial objects can brighten and dim as they rotate, presenting different faces to our telescopes. Comets typically show predictable brightness changes as their irregular nuclei tumble through space, reflecting varying amounts of sunlight toward Earth. But Atlas displayed brightness variations that were more complex than expected. Instead of the relatively simple pattern you might expect from a single rotating object, the light curves showed subtle but persistent irregularities. There were moments when the comet appeared slightly brighter than predicted, and others when it seemed fractionally dimmer, as if something was occasionally blocking or enhancing the light in ways that a solitary nucleus couldn't easily explain. Even more intriguing were the spectroscopic observations, the detailed analysis of the light coming from Atlas that reveals the chemical composition of the gases surrounding it. As the comet warmed in our sun's embrace, releasing its ancient ices into space, astronomers detected something unexpected in the spectrum of that released material. The distribution of gases around Atlas wasn't quite uniform, as you might expect from a single source. Instead, there appeared to be subtle variations in composition and density that suggested multiple points of origin within the comet's coma. Let your mind drift with this mystery as we consider what these observations might mean. Imagine trying to solve a puzzle where each piece of evidence seems to whisper that something more complex is happening than meets the eye. The gravitational perturbations, the brightness anomalies, the spectroscopic irregularities. Individually, each could be explained away, but together, they began to paint a picture that challenged the simple narrative of a lone wanderer from the stars. The timing of these anomalies added another layer of intrigue. The deviations in Atlas's path weren't random. They showed a subtle periodicity, a rhythm that suggested some kind of internal structure or systematic process was influencing the comet's behavior. It was as if Atlas was keeping time to a cosmic metronome that astronomers couldn't quite identify. Perhaps most puzzling of all were the occasional reports from different observatories of slight discrepancies in Atlas's apparent size and shape. While these variations were at the very edge of what our telescopes could reliably detect, some observers noted moments when the comet's nucleus appeared slightly elongated, or when the central condensation of its coma seemed to show subtle asymmetries that couldn't be easily attributed to the usual processes of cometary outgassing. These observations forced astronomers to confront an uncomfortable question. What if their initial assessment had been too hasty? What if the assumption that Atlas was a single monolithic object was wrong? The evidence was subtle, requiring the most careful analysis and the most sensitive instruments to detect, but it was persistent enough that it couldn't simply be dismissed. Consider the implications as you rest in this moment of uncertainty. Here was an object that had traveled for potentially millions of years through the cold emptiness between stars, arriving in our solar system with what appeared to be a perfectly ordinary story. Yet the more closely scientists examined it, the more it seemed to harbor secrets that challenged their understanding of what an interstellar visitor should be. The mystery deepened when researchers began comparing Atlas to the other interstellar objects we'd observed. Oumuamua had shown its own anomalies, unexpected acceleration that couldn't be fully explained by conventional outgassing. Borisov had appeared more straightforward, behaving much like comets from our own solar system. But now, Atlas seemed to occupy a middle ground, displaying subtle complexities that were easier to detect than Oumuamua's dramatic deviations, but more persistent than Borisov's conventional behavior. What was it about these visitors from other star systems that seemed to challenge our expectations? Were we missing something fundamental about the nature of interstellar objects? Or was there something specific about Atlas that made it different from what we thought we understood? As these questions multiplied, astronomers found themselves facing a puzzle that went to the heart of how we understand objects in space. The comfortable certainty that Atlas was simply a lone comet making a solitary journey began to give way to something more complex and intriguing, a mystery that would require them to consider possibilities they hadn't initially imagined. As astronomers delved deeper into the Atlas mystery, the complexity of what they were observing began to reveal just how extraordinary this situation truly was. Let your mind settle into the profound quiet of deep space as we explore why these subtle anomalies were far more significant than they initially appeared. To understand the true magnitude of what researchers were seeing, we need to appreciate the incredible precision required to detect these variations at all. Imagine trying to measure the wobble of a grain of sand from a distance of several city blocks. While that grain is moving at tremendous speed through a medium filled with other particles and forces. This gives you some sense of the observational challenge that astronomers faced when studying Atlas. The gravitational perturbations we mentioned were measured in fractions of arc seconds, angular measurements so small that they represent changes in position that would be invisible to anything but our most sophisticated instruments. To put this in perspective, these deviations were roughly equivalent to detecting the width of a human hair from a distance of several kilometers. The fact that multiple observatories were consistently recording these minute variations suggested that something real and systematic was influencing Atlas's motion. But here's what made these observations so puzzling. The mathematical models that astronomers use to predict comet behavior are extraordinarily precise. They account for the gravitational influence of all the major planets, the pressure of solar radiation, the recoil effect of gas jets escaping from the comet's surface, and dozens of other subtle forces. These models have been refined over centuries of observation and can typically predict a comet's position to within remarkable accuracy. Yet Atlas consistently deviated from these predictions in ways that couldn't be explained by any single factor the models included. The deviations weren't random. They showed patterns that suggested some kind of internal structure or process that the standard models simply didn't account for. It was as if Atlas was following rules that were slightly different from those governing every other comet we'd ever studied. The brightness variations presented an equally perplexing challenge. When astronomers analyzed the light curves in detail, they discovered that the irregularities weren't just random fluctuations. They showed a complex periodicity that suggested multiple overlapping cycles. Imagine listening to a musical chord where you can hear several different notes harmonizing together, each with its own frequency and timing. The brightness patterns from Atlas resembled something similar. Multiple periodic signals combining to create a complex overall pattern. Statistical analysis revealed that the probability of these brightness variations occurring by chance in a single solid object was remarkably low. The patterns were too regular, too persistent, and too complex to be easily explained by the irregular shape and rotation of a typical comet nucleus. Something about Atlas's structure or composition was creating these multi-layered brightness cycles in ways that challenged conventional understanding. The spectroscopic data added another layer of improbability to the puzzle. When astronomers analyzed the chemical signatures of the gases surrounding Atlas, they found that different regions of the coma showed slightly different compositions at different times. This wasn't simply the expected variation you might see as different parts of an irregular nucleus were exposed to sunlight. The patterns were too systematic and too persistent for such a simple explanation. More intriguingly, the spectroscopic variations seemed to correlate with some of the brightness anomalies and gravitational perturbations. It was as if whatever was causing one type of irregularity was also influencing the others, suggesting that all these seemingly separate phenomena might be connected by some underlying structure or process that wasn't immediately apparent. The thermal observations provided yet another piece of the puzzle that didn't quite fit. As Atlas approached the sun and its surface began to warm, infrared telescopes detected temperature variations across the comet that were more complex than expected. Instead of the relatively simple heating pattern you'd expect from a single object with an irregular but unified surface, the thermal signature suggested regions that were warming and cooling at different rates, almost as if they were partially independent of each other. Perhaps most remarkably, when researchers attempted to model Atlas as a single, coherent object and account for all the observed anomalies simultaneously, they found it virtually impossible to create a consistent picture. Any explanation that could account for the gravitational perturbations would predict brightness variations different from what was observed. Models that matched the spectroscopic data couldn't reproduce the thermal patterns. It was as if Atlas was presenting astronomers with multiple, seemingly contradictory sets of evidence about its nature. The cumulative improbability of all these factors occurring together in a single, simple object was staggering. Statisticians calculated that the chances of a conventional comet displaying all of Atlas's observed characteristics simultaneously were vanishingly small, so small that it forced researchers to seriously consider whether their fundamental assumptions about what they were observing might be incorrect. This realization was particularly striking when compared to the behavior of other comets. In our solar system's extensive catalog of comet observations, spanning centuries of increasingly sophisticated measurements, no object had ever displayed such a persistent combination of subtle but systematic anomalies. Even the other interstellar visitors, Oumuamua and Borisov, hadn't shown this particular pattern of multifaceted irregularities. The mystery deepened when astronomers realized that all of these anomalies had been present from the very beginning of Atlas's observation period. This wasn't a case of something changing as the comet evolved during its passage through our solar system. Whatever was causing these effects had been consistent throughout the entire time Atlas had been under study. This suggested that the underlying cause was fundamental to the object's structure, not a temporary or evolving phenomenon. As the weight of this evidence accumulated, astronomers found themselves confronting a profound question. If Atlas wasn't behaving like a single, unified object, then what exactly were they observing? The conventional explanation, a lone comet nucleus traveling through space, seemed increasingly inadequate to explain the complex, multi-layered patterns emerging from the data. The implications were both exciting and unsettling, suggesting that our understanding of interstellar objects might need to be fundamentally reconsidered. Faced with these puzzling observations that seemed to defy conventional explanation, astronomers began to explore possibilities that would have seemed extraordinary just months earlier. As you rest comfortably in this moment, let your imagination drift with us into realms of speculation that challenge everything we thought we knew about solitary travelers from the stars. What if Atlas wasn't alone at all? What if what appeared to be a single comet was actually something far more complex and remarkable? A system of multiple objects traveling together through the cosmic deep? This possibility, once considered, began to illuminate the mysterious patterns in ways that no single object model could achieve. Imagine, if you will, not one ancient wanderer making its way through our solar system, but a small family of cosmic companions bound together by the gentlest gravitational embrace, journeying as one through the endless night between stars. The concept of a binary comet system, two or more objects orbiting their common center of mass while traveling together through space, wasn't entirely unprecedented in our solar system. We've observed asteroid pairs and even some comets that appeared to be fragments of larger bodies still traveling in close formation. But the idea of such a system surviving the millions-year journey through interstellar space seemed almost impossibly delicate and rare. Yet this hypothesis suddenly made sense of observations that had seemed contradictory. Picture two comet nuclei, perhaps separated by only a few kilometers, each following its own subtle orbital dance around their shared gravitational center, while the entire system moved through our solar system. The tiny perturbations in Atlas's path could be explained by this internal orbital motion, the gentle gravitational tug-of-war between companions, creating the minute deviations that had puzzled astronomers. The complex brightness variations, too, found new meaning in this framework. Instead of trying to explain multiple overlapping periodic signals from a single rotating object, imagine the elegant interplay of two separate bodies, each with its own rotation period, each occasionally eclipsing or enhancing the other's reflected light. The multi-layered brightness patterns that had seemed so improbable for a single object became natural consequences of a binary system's complex dance. Even more intriguingly, the spectroscopic variations began to make sense. If Atlas consisted of two objects with slightly different compositions, perhaps fragments of different regions from their parent body, or objects that had formed under slightly different conditions in their distant stellar nursery, then the varying chemical signatures in the coma could represent the different contributions of each component as they outgassed at different rates and times. But the binary hypothesis led to even more fascinating possibilities. What if the objects weren't just gravitationally bound fragments, but represented something even more remarkable? Some researchers began to wonder if Atlas might be an example of a contact binary. Two objects that had been orbiting each other for so long that they occasionally touched, creating a dumbbell-shaped structure that could separate and reconnect as gravitational and rotational forces shifted the system's configuration. This scenario could explain the thermal variations that had seemed so puzzling. A contact binary system might show different heating patterns as solar radiation affected the connected and separated phases differently, creating the complex temperature signatures that infrared telescopes had detected. Another possibility that emerged from theoretical modeling was even more exotic. What if Atlas represented a rubble pile system? Not two discrete objects, but a loose collection of smaller fragments held together by mutual gravity, creating a structure that was neither fully unified nor completely separate. Such a system might behave almost like a fluid, with components shifting and rearranging themselves in response to the changing gravitational and thermal environment as the system traveled through our solar system. The rubble pile hypothesis offered explanations for observations that even the binary model couldn't fully address. The subtle but persistent changes in Atlas's apparent shape and size could represent real structural evolution, as the loose collection of fragments responded to solar heating and tidal forces, constantly reconfiguring itself while maintaining its overall integrity as a traveling system. Perhaps most remarkably, some theorists proposed that Atlas might represent something unprecedented: a convoy system of multiple small objects traveling together, not because they were gravitationally bound, but because they shared similar trajectories from their common origin. Imagine a small fleet of cosmic wanderers born from the same catastrophic event in a distant star system, following nearly identical paths through interstellar space with such precision that they appeared to be a single object from our distant vantage point. This convoy hypothesis could explain why the various anomalies seemed correlated but not perfectly synchronized. If multiple objects were traveling in loose formation, occasionally approaching each other closely enough to create the appearance of a single, complex system, then separating again to reveal their individual characteristics, it might produce exactly the kind of variable, multifaceted behavior that Atlas had displayed. Each of these alternative perspectives required astronomers to expand their thinking about what was possible in the realm of interstellar objects. The idea that such complex, multi-component systems could survive the journey between stars challenged assumptions about the harsh realities of interstellar space. The cold, the radiation, the gravitational perturbations from passing stars. All of these factors should, in theory, tear apart any delicate gravitational relationships over the millions of years required for interstellar travel. Yet here was Atlas, potentially proving that the cosmos was capable of preserving and delivering to our doorstep structures far more intricate and remarkable than anyone had imagined possible. If any of these hypotheses were correct, Atlas wasn't just a visitor from another star system. It was a messenger carrying information about the delicate gravitational architectures that could persist across the vast emptiness between worlds. The implications extended beyond Atlas itself. If one interstellar object could be a complex, multi-component system, how many others might be as well? Had we been systematically underestimating the diversity and complexity of the cosmic traffic flowing through our solar system, seeing only single objects where nature had actually crafted intricate, traveling communities of companions? If Atlas truly represents a complex, multi-component system, rather than a solitary wanderer, the implications ripple outward through our understanding of the cosmos in ways both profound and beautiful. Let your mind drift peacefully as we explore how this possibility transforms not just our view of one mysterious visitor, but our entire conception of the universe's hidden architectures. Consider first what this would mean for our understanding of planetary system formation. If Atlas is indeed a binary system, contact binary, or traveling convoy that survived millions of years of interstellar journey, it suggests that the processes that create and destroy worlds are far more nuanced than we previously imagined. The delicate gravitational relationships we've been contemplating would have had to survive not just the original catastrophe that ejected them from their home system, but also the long, cold passage through the void where even the slightest perturbation from a passing star could have torn them apart. This resilience implies that nature possesses mechanisms for preserving complex structures across scales of time and distance that challenge our assumptions about cosmic fragility. If such delicate gravitational architectures can persist through interstellar space, What other intricate arrangements might be traveling unseen through the galaxy? The cosmos may be far more richly structured, far more artfully organized than our models of random collisions and gravitational disruption have suggested. The implications extend to our understanding of how information travels between star systems. If Atlas carries within its structure clues about the conditions in its distant birthplace, perhaps in the different compositions of its components, or in the precise dynamics of their orbital relationship, then it represents something unprecedented, a detailed message from another stellar neighborhood, encoded in the very architecture of matter and motion. This transforms interstellar objects from simple curiosities into potential libraries of information about distant worlds. Each binary system, each contact binary, each traveling convoy becomes a messenger, carrying news of conditions around other stars, of the processes that shape planetary systems throughout the galaxy, of the myriad ways that matter can organize itself when given millions of years to find stable configurations. But the ramifications reach even deeper into questions about the prevalence of complex systems in the universe. If our solar system is regularly visited by multi-component interstellar objects, it suggests that the galaxy is filled with traveling communities of various sizes and configurations. Some might be binary pairs, like we've imagined for Atlas. Others might be larger families, 3, 4, or even more objects bound together in gravitational relationships of stunning complexity and beauty. This possibility reframes our search for life in the universe in intriguing ways. If nature can preserve delicate gravitational relationships across interstellar distances and timescales, what does this suggest about its ability to preserve other forms of complexity? The same processes that might allow Atlas to maintain its multi-component structure could potentially protect more elaborate arrangements of matter, perhaps even arrangements complex enough to support or preserve biological information. The discovery also has profound implications for our future as a spacefaring species. If the galaxy is populated with traveling systems of multiple objects, then the space between stars is not the empty void we once imagined, but rather a network of moving communities, each following its own trajectory through the cosmic deep. Understanding these systems, their dynamics, their origins, their destinations, becomes crucial for navigation and safety as we eventually venture beyond our own solar system. Moreover, if we can learn to detect and characterize multi-component interstellar objects more effectively, we gain a new tool for studying distant star systems. Each traveling system becomes a sample of another world, carrying physical evidence of conditions around other stars directly to our instruments. Instead of relying solely on the faint light from distant exoplanets, we could study actual material from other stellar neighborhoods, analyzing its composition and structure to understand how planetary systems form and evolve throughout the galaxy. The Atlas mystery also suggests that our current methods for detecting and studying interstellar objects may be fundamentally incomplete. If we've been assuming that these visitors are simple, monolithic bodies when many of them are actually complex systems, then we've been missing crucial information about their nature and origins. This realization calls for new observational strategies, new theoretical frameworks, and new ways of thinking about what we might find when we look more carefully at the cosmos. Perhaps most profoundly, the possibility that Atlas is not alone challenges our deepest assumptions about isolation and companionship in the universe. The image of solitary objects drifting alone through the cosmic void has long served as a metaphor for the existential loneliness that many feel when contemplating our place in the cosmos. But if Atlas teaches us that even the most ancient wanderers can maintain companionship across millions of years and vast distances. It suggests that the universe may be fundamentally more connected, more community-oriented than we ever dared imagine. This perspective transforms our understanding of what it means to journey through space and time. Instead of seeing cosmic evolution as a process of increasing isolation and entropy, we begin to glimpse possibilities for persistent connection, for communities that endure across scales that dwarf human experience, for relationships that survive even the death of the worlds where they were born. The implications cascade through our understanding of physics, astronomy, and even philosophy. If delicate gravitational relationships can persist across such vast scales of space and time, what does this tell us about the fundamental nature of connection in the universe? What other forms of relationship and community might exist at scales we haven't yet learned to perceive? As we contemplate these possibilities, Atlas becomes more than just an interstellar visitor. It becomes a symbol of the universe's capacity for preserving complexity, maintaining relationships, and delivering messages across the vast distances that separate worlds. Whether binary, contact binary, or traveling convoy, it represents proof that even in the apparent emptiness between stars, community and companionship can endure. As we reach the end of our journey through the mystery of 3I Atlas, let your breathing settle into its deepest, most peaceful rhythm. We began tonight with a simple image, a lone comet drifting through our solar system, following the predictable paths that celestial mechanics had taught us to expect. Yet, as we've discovered together, the universe rarely offers such simple stories to those who look closely enough to see its hidden complexities. Our exploration has taken us from that initial picture of solitary wandering to something far more profound and beautiful. We started with Atlas as a single, ancient traveler, making its once-in-a-lifetime passage through our cosmic neighborhood, a familiar narrative that fit comfortably within our understanding of how interstellar objects should behave. But the subtle anomalies we discovered, those tiny gravitational perturbations, the complex brightness variations, the puzzling spectroscopic signatures, gradually revealed that this comfortable narrative was incomplete. The evidence that accumulated challenged every assumption about Atlas being alone. The mathematical improbability of all these anomalies occurring in a single, simple object forced us to consider possibilities that would have seemed extraordinary when we began our journey. The persistent patterns in the data, the correlations between different types of observations, the systematic nature of the deviations, all pointed towards something more complex and remarkable than anyone had initially imagined. Through our exploration of alternative perspectives, we discovered that Atlas might represent something unprecedented, a multi-component system that had somehow maintained its delicate gravitational relationships across the vast distances and immense timescales of interstellar travel. Whether as a binary pair, a contact binary, a rubble pile, or a traveling convoy, Atlas emerged not as a solitary wanderer, but as a community of companions journeying together through the cosmic deep. This transformation in our understanding carries with it the most compelling argument for reconsidering how we view the universe itself. If Atlas is indeed not alone, if it represents a complex system of gravitationally bound objects that survived millions of years of interstellar journey, then it demonstrates that the cosmos possesses mechanisms for preserving intricate structures across scales of time and distance that dwarf human experience. The implications ripple outward through every aspect of our cosmic perspective. Our galaxy may be filled not with isolated, lonely objects drifting alone through the void, but with traveling communities of various sizes and configurations, each carrying within its structure a detailed message about distant stellar neighborhoods. The space between stars transforms from empty wasteland to a network of moving relationships, each following its own trajectory through the cosmic deep. This revelation suggests that complexity and companionship may be far more fundamental features of the universe than we ever dared imagine. If delicate gravitational relationships can endure across such vast scales, what other forms of connection and community might exist at levels we haven't yet learned to perceive? The universe begins to appear not as a collection of isolated objects gradually succumbing to entropy, but as an intricate web of relationships that can persist and evolve across cosmic time. Perhaps most profoundly, Atlas challenges our deepest assumptions about isolation in the cosmos. The image of solitary objects drifting alone through infinite darkness has long served as a metaphor for existential loneliness, the sense that we are fundamentally alone in an indifferent universe. But if even the most ancient wanderers can maintain companionship across millions of years and unimaginable distances, then the universe reveals itself as fundamentally more connected, more community-oriented than our loneliest fears have suggested. As you rest in this moment of deep relaxation, consider what this means for our own journey through space and time. We travel together on our small planet, bound by gravitational relationships that are themselves part of larger systems: our solar system, our galaxy, our local group of galaxies, all moving together through the cosmos in patterns of connection that extend far beyond what we can directly perceive. Atlas, whether alone or accompanied, reminds us that we too are part of traveling communities that persist across vast scales. The atoms in our bodies were forged in stellar furnaces and scattered through space by ancient supernovas, eventually finding their way into the gravitational embrace of our solar system, our planet, and ultimately into the complex arrangements that allow us to contemplate these cosmic mysteries. The story of Atlas, from apparent solitude to possible companionship, mirrors our own growing understanding of connection in the universe. What appears isolated often reveals itself, upon closer examination, to be part of larger patterns of relationship and community. The lone comet becomes a binary system. The isolated star system becomes part of a galactic community. The seemingly empty space between worlds becomes a network of traveling relationships. In the end, the question of whether Atlas is truly alone may be less important than what the possibility of its companionship teaches us about the nature of connection itself. Even if future observations reveal that Atlas is indeed a single, unified object, the fact that its behavior led us to seriously consider multi-component alternatives has already expanded our understanding of what's possible in the cosmos. The universe, as revealed through the mystery of Atlas, appears to be a place where companionship can endure across the vastest distances and longest timescales, where complex relationships can survive journeys that span millions of years, where even the most ancient wanderers need not travel alone through the infinite night. As you drift toward sleep, carry with you this image. Somewhere in the darkness between stars, communities of objects continue their patient journeys, bound together by forces so gentle they can barely be measured, yet so persistent they can survive the death of the worlds where they were born. In a universe capable of such enduring companionship, perhaps none of us, whether comet or human, planet or star, ever truly travels alone.